In this video, I'm going to solve a problem that's very similar to one that you do in the homework. In your homework assignment, you are asked to show that the centroid of a triangle with certain vertices is the point of intersection of the medians of that triangle. My problem is similar. I'm going to show that the centroid of a parallelogram with the vertices shown is the point of intersection of the diagonals. So this is what I'm trying to prove. I haven't proved it yet, but I'm taking this diagonal and this diagonal, and I want to show that it's going to be that point right there. So first, I think I'm just going to derive the formulas for the mass of this thing, the mass of my parallelogram, as well as the moments of my parallelogram, so I can come up with formulas for the center of mass. So this is the point A0, and this is the point A plus B, that's my x value, and y is equal to c. And over here we're at the point BC. Just looking at this picture, when I'm thinking about center of mass, I know that I want to slice it this way because my function on the right and my function on the left are going to be the same, and we're going to integrate from this y value, which is 0, all the way up to this y value, which is c. So it makes the most sense to me to do that as opposed to slicing this way, and I would have a top function like this over here, and then I have a different top function for a while, and then I have a top function here, and then a bottom function here. It gets complicated. But if I slice this way, if those are my representative rectangles, I end up with this function on the right the whole time and this function on the left. So I think that's going to make the most sense for me as far as coming up with the formulas for the mass and the moments for this parallelogram. Okay, so what have we got here? Well, I know mass is equal to density times area. Density is mass per unit area. And since we're looking for a centroid, we can just assume that the density is equal to 1. I just wrote the wrong Greek letter here. It's rho equals 1. So we're going to assume density equals 1, so the mass and the area are going to be exactly the same thing. So to find the area, well, I'm going to integrate from this y value to this y value, so from 0 to c. And I need the top function minus the bottom function. Or, since we're integrating with respect to y, I need x on the right minus x on the left. And these aren't too bad, they're just lines. They look bad because of these a's and b's and c's. I'm having trouble writing this evening. Okay. But it's really not too bad at all. The equation of this line is simple. It goes through the origin, so I know the y-intercept is 0, and the slope is, well, I go up c and over b units. So this line is given by y equals rise over run, so c over b times x. So that's x on the, or that's the formula for the equation of this line on the left. But I need x on the left as a function of y. So I'm going to multiply both sides by the reciprocal of this. If y is c over b times x, I flip this and multiply, I get x is b over c times y. So that's good. All right, and similarly, we see we have a line with the same slope. Over here, rise over run is still b, so I'm going up b units, or excuse me, up c units, this is up c, and then we're going to the right b units, so that's a, and then this is a plus b. So the equation of this line is y equals the slope, so we go rise over run, so we go c over b times x, plus a constant. Now, I'm just going to write constant for right now. to make it easier for us because we're using the letter B for something else. When x equals a, y has to equal 0. So I'm going to substitute in, a for x and 0 for y. And we kind of get an ugly constant, don't we? So that constant, which would traditionally be our y-intercept, it's just going to be negative AC over b. Ugh, looks kind of ugly. So I have y is equal to c over b times x minus AC over b. And I need x as a function of y on that line because I need x on the right. So I'm going to solve this for x. So I have y, I'm going to add that to both sides. Y plus AC over b equals c over b times x. And then we're going to multiply both sides by the reciprocal, so multiply by b over c. Those reduce, distribute, distribute. And you get x equals b over c times y plus a times c over b times b over c. Those reduce, and we end up with b over c times y plus a. And that's convenient. Look what happens. Because those had the same slope, and that's going to happen because it's a parallelogram, I end up with something that looks like this. That's my first line, some slope times y plus a, and I'm subtracting the second line. It has the same slope times y. So these guys reduce, and I'm just integrating a with respect to y. According to my formulas, the antiderivative of a constant with respect to y is just a constant times a variable. You integrate from y equals 0 to y equals c, so you get AC. That is the area of the region, or the mass now. It's like, huh, okay, that's simplified pretty nicely. Not too bad at all. All right, now we want to find the moment about the x-axis. Now we're assuming that we have a constant density. Actually, let me write down my formulas. It always helps me to write down my formulas. This is going to be mass times the distance to the x-axis. And we have density times area times distance to the x-axis. That'll work. And our density is 1. Because we're just assuming that it's 1 to make it simple. So we've got the area formula times our distance. Now the distance to the x-axis, when I look at this picture here, I see my distance to the x-axis. It's the distance from there to there. Well, that's just y. So my area is the x function on the right minus x on the left times delta y, because I see that. X on the right minus x on the left times delta y is my area, and then the distance is just y sub I. X on the right, we found earlier, that was this. X on the left was this. So every time we have x right minus x left, those two terms are going to cancel, and we just get a. So this distance is a constant a the whole time, which I think is pretty cool. But I guess that's just a property of a parallelogram. Times y sub I times delta y. So the mass about the x-axis for this, or excuse me, moment about the x-axis for this particular rectangle is just a times y, and we're multiplying by delta y. So the moment about the x-axis for the whole thing is just the integral of ay with respect to y, and we're integrating from 0 to c. So we bring our constant down, add 1 to the exponent, divide by the new exponent, plug in 0 and c and subtract, and it looks like we get 1/2 ac squared as our moment about the x-axis. Now for the moment about the y-axis, well, we're going to take our mass, which is the same as our area in this case because our density is 1, and we're going to multiply by the distance to the y-axis. The distance to the y-axis is the average x value. So the formula for that is going to be the integral from 0 to c of 1/2. And when we take the average x value, we're going to have x on the right minus x on the, or x on the right plus x on the left. And we divide by 2 to get the average. For the area, we're going to have x on the right minus x on the left. So what ends up happening is we get x on the right squared, and we subtract x on the left squared. X on the left was just this line, and x on the right was this line. And that just comes from the algebra. Or if you prefer, you could find that distance to the y-axis and find the area and then simplify everything algebraically, and it's going to cancel. It's going to be exactly the same thing as this. Our density is 1, so that's not shown here. So I'm going to integrate this. I get b over c times y squared plus 2 of these, 2 abc over y plus a squared, and I'm subtracting b over c times y squared. So these guys reduce, those are gone. This one's more complicated, isn't it? So I have the 1/2, and I bring down my constant, and I add 1 to the exponent and divide by the new exponent. So those 2's are going to reduce. And a squared is just a constant, so I have a squared times my variable, and we're integrating from 0 to c. Whew, it's looking pretty bad. But it's going to simplify quite nicely in just a moment. Alright, so the moment about the y-axis is this. We've got 1/2. I've got ab over c times c squared plus a squared times c, and when we substitute 0, we just get 0. So one of those c's is going to reduce, and we just get 1/2 abc plus a squared c. Okay, so I've got moment about the x-axis and moment about the y-axis, and I've got the mass. So I can put all those together to find my center of mass. Moment about the y-axis was this kind of ugly thing. And I'm dividing everything by the total mass, which was AC. And for the moment about the x-axis, I've got this. I'm dividing by the total mass. So an AC is going to reduce from both of those. I'm going to factor it out. I get AC times 1/2 B. Or actually, let's keep the 1/2 out front too. I have 1/2 AC times B plus, if I factor out an AC, I'm still left with an A in there. All of that's divided by AC. Here I've got an AC times 1/2 and an extra C. I've got this and this. The ACs reduce, and my center of mass, or centroid, is 1/2 of A plus B and 1/2 of C. And say, okay, well, what does that have to do with the original question? The claim is that the centroid lies on the line of, or the point of intersection of these two diagonals. And from what I just found, x bar y bar was 1/2 of A plus B and 1/2 of C. Now the 1/2 C makes a lot of sense, because if this is C, wouldn't you expect the centroid, or the y-coordinate of the center of mass, to be half of that, because we're going from 0 to C, it's like the average. I would expect that. And this looks like I took A and I took B, I added those and I took their average. Well, I'm not really sure how that would come into play here. So this is what I calculated. Now I want to show that the point of intersection of this line with this line is the same as this. So I just need to find the equations of those two lines. And it's not too bad, it's just lines, guys. Don't be intimidated by a little line. Okay, we're right here. First, let's find that line, the equation of that line. So I want this guy, that line right there. Well, let's think about what the slope would have to be. Well, it's going to have a negative slope, right? Because as I look at it from left to right, it goes down. And we are, that's y equals c. So we're falling c units. And we're running to the right this distance. Well, this is x equals a and that's x equals b. So I think that distance is this x value minus that smaller x value. So it's going to be a minus b. So this yellow line has a slope of rise or fall over run times x plus a constant. I'm just going to use capital A for right now because we've already used b for something else. To figure out what that is, I'm going to use this point, a0. When x equals a, y has to be 0. So I've got, if x equals a, I'm going to have a negative ac in the numerator over a minus b. So capital A must be the opposite of this. So if I add that to the other side, I get capital A equals AC minus A minus B, or AC over A minus B. Whew, so the equation of that line is y equals negative C over A minus B times x plus AC over A minus B. Or if you prefer, let's make it a little simpler even. Get a common denominator. I'm going to factor out a negative c. So I've got negative c here times x gives me the first term. Negative c times negative a gives me the second one. Ah, actually that makes a lot of sense. Do you see why? It's just like point slope form. There's my slope, and I've got x minus a and equals y minus the corresponding y value, which is 0. Okay, so that's the equation of the yellow line. I'm going to highlight that in yellow just to remind myself what it was we calculated over here. Alright. Now I want to see where that intersects this other one. So let's draw this line. This one's going to be easier. It goes through the origin. That's nice. So the slope is easy on this one. We go over this many units and up this many units. Well, we're running to the right, a plus b, and we're going up c units. So the equation of this line, which I need another highlighter, this enormous bag of markers, which I think is kind of funny. Let's see. There we go. I want the pink line now. That line has a y-intercept of 0. So we go to the right a plus b units and up c units. So it's rise over run, c over a plus b times x is the equation of the pink line. And now we want to put these two guys together because that point of intersection is when this y value equals this y value, and see what x would have to be. Hopefully x has to be a plus b times 1/2. And then at that particular x value, our y value should be half of c according to the previous work, if everything else went right, if that's correct. Let's see if it is. So we're going to set the y's equal to each other. So the first y is this one, the pink line. The second y is this one. Maybe we want to multiply both sides by a plus b times a minus b. Multiply by the LCD. Let's multiply both sides by a plus b first. Gets rid of that. And now I've got cx over here equals negative x minus a times a plus b all over a minus b. I'm going to multiply both sides by a minus b this time. Woo! There we go. So I've got a minus b times cx equals negative c times x minus a times a plus b. It looks like a mess, but it's actually quite doable. These are just constants, guys. My variable is x. I'm just trying to get x by itself. X appears on both sides. So the first thing we're going to do is get rid of the parentheses by distributing. This is a monomial, so I distribute term by term, and I get acx minus bcx. Over here, I want to distribute the binomial times the binomial first. First times first is ax, outer times outer is bx, inner times inner is negative a squared, and last times last is negative ab. Gosh, it's a lot going on. That's okay. Distribute the negative c. Trust the math. Things sometimes get more complicated before they get very, very easy. So we are willing to tolerate the temporary complication. So I've got minus bx, or bc times x there. Ooh, I'm running out of space. Next line. Negative a squared times negative c is plus a squared c. Negative ab times negative c is abc. Okay, do I have any cancellations? I do. Let's add bcx to both sides. Bam, those are gone. And then let's add acx to both sides. If I add that over there, then I'll have two of them. I'm so close to getting x by itself. So I've got a squared c plus abc, and I want to get x by itself, so I'm going to divide everything by 2ac. Factor out the ac in the numerator. ac times a is the first term, ac times b is the second. Ah, you see it? Bam! X is 1/2 of a plus b, which is what it's supposed to be. That's a very, very good thing. So we found that x value is what it's supposed to be. Let's see if we get the same y value that we're supposed to get. So let's substitute in this x value to both of these and make sure that it works out to be exactly what it's supposed to be. Now when I substitute x equals 1/2 a plus b here, we're just checking. I'm replacing x with 1/2 of a plus b. That reduces and that reduces, and I just get 1/2 of c. Awesome, that's exactly what I was supposed to get. The other one looks very complicated, but we're still going to check it out. So we're not going to take any of this stuff for granted. Hey, we might be wrong. We may have made a mistake somewhere. You always want to be sure. We're okay. Sometimes we make mistakes. That's fine. Problem solving is still fun. We learn so much from the mistakes we make. We learn so much more from mistakes than we learn from other things. So we're going to distribute the 1/2 there, and we get negative c times the quantity 1/2 a, and then I have a 1/2 b, and I'm adding those, and I'm subtracting a, all over a minus b. Okay. Then 1/2 a minus an a is going to be a negative 1/2 a. So I have 1/2 b minus 1/2 a, all divided by a minus b. And if I factor out a negative 1/2 here, watch what happens. A negative times a negative is going to make that a positive 1/2 times c. If I factor out a negative 1/2, I'm left with a negative b. If I factor out a negative 1/2 here, I'm left with a positive a. A negative b plus a is the same as a minus b. So those reduce, and what do you know? Y is 1/2 of c. So these two diagonals, they intersect at this point, and that point has coordinates 1/2 a plus b and 1/2 of c. And that is beautiful. You might say, why on earth is that beautiful, Miss Townsend? Because anytime we've got a parallelogram like this, and we can put the origin anywhere we want. Once we locate that origin and draw one of our axes in such a way that it's parallel with one of the sides, we've got a formula for the centroid every time. So you're going to do something similar. You are asked to show that the centroid of a triangle with certain vertices lies at the point of intersection of the medians, and you're going to follow a similar procedure. First, you're going to find the moments about the x and y axis and the mass. You're going to find the center of mass. It's going to be a formula in terms of the coordinates of those vertices. I've got vertices of a parallelogram. You're going to have vertices of a triangle. And then you're going to have to show that the point where those medians intersect in the triangle problem actually is the point that you came up with the other way. So this is a fun exploration. Most of the problems in engineering take advantage of these formulas, so I think it's a really good idea to at least go through the derivation once and see where they come from. And then once you know where they come from, you don't have to derive them over and over again every time. You can just use the formulas after that. So I hope this helps you with the related homework problem.